You ever wonder how an AI can just master a game like chess without anyone giving it an instruction manual? I mean, it just learns by trial and error, right? But on a scale of millions, even billions of tries. Well, today we're going to dive into that whole fascinating story. This is the evolution of smart algorithms, a journey into what's called reinforcement learning.
All right, so here's our game plan. We're going to start with the basic problem, what I'm calling the learning robot's dilemma. Then we'll check out two really different ways to learn, one cautious, one, well, pretty optimistic. After that, we'll see why those early ideas just weren't enough and how that led to a huge upgrade, basically giving the AI a real brain. And finally, we'll pull it all together for a big picture recap. Sound good? Let's do it.
Okay, first up, the learning robot's dilemma. Seriously, picture this. You drop a brand new robot into a maze. It knows it needs to get to the end, but you haven't given it a map, no instructions, nothing. All it can do is just try stuff. Go left, hit a wall, go right, find a dead end. That, right there, is the fundamental problem in all of reinforcement learning.
So it all boils down to this one big question, right? How does an AI learn to win a game when it doesn't even know the rules? The AI, or as we call it, the agent, it has to figure out the absolute best move to make at any given moment to get the biggest possible reward in the long run. And here's the kicker. It has to do all of this without anyone telling it what's good or bad. It's learning the value of everything completely from scratch.
All right, so once our little agent starts stumbling around and learning, you immediately hit this almost philosophical fork in the road. How should it actually learn? Should it be super cautious, learning from every single mistake it makes? Or should it be an optimist, always looking at the best possible outcome, kind of ignoring its own clumsy steps? This is a huge debate, and it gives us our first two big competing strategies.
And this really sets up the two personalities we're talking about. On one side, you've got Sarsa. Think of Sarsa as the realist. It's grounded. It learns from what it actually does, mistakes and all. Then you've got Q-learning, the total optimist. It doesn't care about the clumsy step it just took. It learns based on the perfect, best-case scenario move it could have made from that spot. Two totally different philosophies.
So let's break down Sarsa first. It's what's called on policy, which is just a fancy way of saying it learns based on the policy or the strategy it's following right now. So if its current strategy involves a bit of, random, clumsy wandering to explore, Sarsa takes that into account. It knows it might mess up, so it factors that risk right into its learning. It's conservative. It's safe.
And the cliff walking problem is the perfect example of why this matters. Okay, so you have an agent that needs to get from one end of a cliff to the other. The shortest path is right along the edge, but what does Sarsa do? It learns to take the longer, safer path way back from the edge. And why would it do that? Because it knows its own strategy isn't perfect yet. It knows there's a chance its explore move could be step right off the cliff. So it plays it safe. It literally plans around its own potential mistakes.
Q-learning, though, totally different beast. It's off policy. It completely ignores its current, clumsy strategy when it learns. Instead, it looks at a situation and asks, forget what I'm doing now, what is the absolute best move anyone could ever make from this spot? It's learning about the perfect, optimal path, even while it's still tripping over its own feet. It's incredibly ambitious, but as you might guess, there's a pretty big catch.
And here it is, the problem with being a total optimist. It's called maximization bias. Because Q-learning always assumes the best possible outcome, it can get greedy and a little dumb. Imagine there's a row of slot machines and one of them is noisy and pays out a big jackpot once, just by pure random luck. Q-learning sees that one big payout, overestimates the value of that machine, and will just keep pumping coins into it forever, convinced it's a winner. That overestimation, that's maximization bias, and it's a huge problem.
Okay, so for a while, both Sarsa and Q-learning were doing great. For simple games, they had a neat trick. They just stored everything they learned in a giant chart, a big lookup table. But what happens when the game isn't simple anymore? What happens when the world gets huge? Well, that's when this simple little table becomes an impossible roadblock. This lookup table, or Q table, is basically a cheat sheet for the game. Imagine for every single square on a tic-tac-toe board, you have a little note that says, move here, scores 10, move there, scores 5. The agent just looks at where it is, finds the entry on its cheat sheet, and picks the move with the highest score. Super simple, super direct. For little grid world games, it's perfect.
But then, you try to do this for the game of Go. The number of possible positions on a Go board is 10 to the power of 170. Let me say that again. That number is bigger than the estimated number of atoms in the entire known universe. You could not build a computer big enough to hold that table. It is physically, fundamentally impossible. The whole idea of a cheat sheet just completely, utterly falls apart.
And this is the moment everything changes. This is the great leap. If you can't memorize every single possible situation, you need something smarter. You need something that can generalize. Something that can look at a board position it has never seen before and still make a really good guess about which moves are good and which are bad. When your cheat sheet is too big, you don't need a better cheat sheet. You need a brain. You need a neural network.
So let's upgrade the brain. We are now officially entering the era of deep reinforcement learning. The groundbreaking idea was to take that old Q-learning optimist and get rid of its lookup table. Instead, we give it a powerful deep neural network to estimate the values. This new hybrid is called a deep Q network, or DQN for short. But it wasn't that easy. You couldn't just swap in a neural network and call it a day. The early attempts were wildly unstable and just didn't work.
But the researchers at DeepMind came up with two incredibly clever fixes that made it all work. First, something called experience replay. Instead of the AI learning from its experiences one by one as they happen, it stores them all in a big memory bank. Then, to learn, it just pulls out random handfuls of these memories. It's like studying for a test using shuffled flashcards instead of reading the textbook cover to cover. It breaks up all the weird correlations. The second trick was a target network. Basically, the AI uses a frozen, slightly older copy of itself to judge its own progress. This brilliant move stops it from, constantly chasing a moving target. It gives it a stable goal to aim for.
And those two hacks together, they were the magic bullet. They made deep reinforcement learning stable and possible. But remember that old problem with Q-learning, that pesky optimism? Well, since DQN was built right on top of Q-learning, it inherited its original flaw. It still had that maximization bias. This new super smart brain was still a little too optimistic for its own good, overestimating the value of lucky breaks.
So the next evolution was called double DQN, and the solution is it's so elegant. The best way to think about it is this. Don't trust one person to select the winner and judge the winner, right? You separate those two jobs. And that's exactly what double DQN does. It uses its main up-to-the-minute network to pick what it thinks is the best next move. But then it asks that older, frozen target network to give an honest, unbiased score for that move. This simple separation of duties finally solved that nagging overestimation problem.
Which brings us to one last major upgrade on our journey, dueling DQN. The big idea here is really clever. It's that sometimes the value of your situation has very little to do with the specific action you take. Like, if you're about to get checkmated, it doesn't really matter which losing move you make, right? The state itself is just bad. So dueling DQN splits its brain into two streams. One stream just figures out how good the current state is in general. The other stream figures out the relative advantage of each possible action. Combining those two gives a much richer, more nuanced understanding of the world, and it helps the AI learn way more efficiently.
Whew. Okay. We have covered a ton of ground here. We went from simple little lookup tables all the way to these complex, dueling neural network brains. So let's just take a breath and recap this whole evolutionary story, putting all the pieces in one place.
All right, here's your cheat sheet for the whole journey. It all started with Sarsa, our safe but slow realist. It was too cautious, so we got Q-learning, the optimist, who aimed for the best but suffered from that maximization bias. When the problems got too big for their tables, DQN stepped in, giving Q-learning a neural network brain and stabilizing it with experience replay and a target network. But it still had that bias, so double DQN fixed the bias for good by decoupling the selection and evaluation. And finally, dueling DQN sped everything up with its smarter architecture that separates the state's value from an action's advantage. You can see it, right? Each new algorithm is a direct answer to the flaws of the one that came before it. It's a beautiful evolution.
So, when you look at this whole story, it's really been about one thing: teaching a machine to learn from its past, to learn from the consequences of its actions. But the next giant leap in AI, the next frontier, is something totally different. And that's the question I want to leave you with. We've taught them to learn from the past. What's it going to take to teach them to imagine the future?